Hello, everyone, my Year 11 physics class. This is the first video in our nuclear fission and fusion series, which is going to take us through this week and next week. The topic for today is binding energy, and it's made up of a few different parts, so let's get started with a bit of an introduction. First of all, let's talk about forces. There are four fundamental forces in the universe. These are the forces that hold everything together. They govern all of the interactions between different particles, and they're kind of what makes the universe work. They're the things that govern all the different laws of the universe, these four fundamental forces. You have heard of at least two of them. There's gravity. That's one of them. There is the electromagnetic force. You've heard of that one as well. That is, even if you don't know it by that name, that is the name of the force that, for example, causes positive and negative charges to be pulled towards each other and like charges to be repelled. That's the electromagnetic force. The two that you might not have heard of are the strong nuclear force and the weak nuclear force. Okay, let's talk about each one of these. So gravity, we know gravity is a force that attracts all matter. Anything with mass is attracted to anything else that has mass through the force of gravity. Now, let's give each of these forces a relative strength. So if gravity had a strength of 1, what would each of the other forces be? The electromagnetic force would have a strength of 10 to the power of 36. In other words, it's 10 to the power of 36 times stronger than gravity. The weak nuclear force has a strength of about 10 to the power of 32, so it's 10 to the power of 32 times stronger than gravity. And the strong nuclear force, obviously, because of its name, is the strongest, and that's 10 to the 40. It's 10 to the power of 40 times stronger than gravity, the force with which it pulls things together. However, the difference, the advantage that gravity has over the strong nuclear force is that gravity can work over very large distances. You know, the Earth and the Sun are affecting each other because of gravity, even though they are very, very far apart. The strong nuclear force, however, which is the one that we're focusing on for the next couple of weeks, the strong nuclear force acts at very short distances. It acts at distances roughly the size of a nucleus and no bigger. And that is because the strong nuclear force is the force that holds nuclei together. It's the force that holds nuclei together. So far we've been talking over the last few weeks about how nuclei are made up of protons and neutrons, positive and neutral charges. And if you just shoved a whole bunch of positive charges and neutral charges together, then all of those positive charges should repel from each other. And we've been speaking about how the neutral charges counteract that, but we haven't really explained how, because really what counteracts a positive charge is a negative charge. Having a whole bunch of positive and neutral charges together still means that everything is a net positive charge, and so all of the things should be separating. Those protons in the nucleus should be flying apart from each other. To counteract that electromagnetic force that is trying to get those protons to rip apart from each other, we have the strong nuclear force, which is the force that binds the nucleus together and keeps everything inside. So that's the force that we're going to be focusing on. Let's talk about where that force comes from. If you look at your formula and data sheet, you will see that the mass of a proton is equal to roughly 1.67 times 10 to the negative 27 kilograms, and the mass of a neutron is the same. They're actually a little bit different, the mass of a proton and the mass of a neutron, but when we write them to three significant figures, they round to the same number, 1.67 by 10 to the negative 27 kilograms. Let's look at a nucleus, like a helium-4 nucleus. So helium-4, it would look like this, if I was to write it using the notation that we've been using. And that helium-4 nucleus is made up of 2 protons and 2 neutrons. So if I was trying to calculate the mass of a helium-4 nucleus, then I would do 1.67 times 10 to the negative 27, and I would do all of that times 4 because that's how many nucleons I have. So if I do 1.67 times 10 to the negative 27 times 4, that gives me a mass of 6.68 times 10 to the negative 27 kilograms. So that number there, 6.68 times 10 to the negative 27 kilograms, is what we would expect the mass of a helium nucleus to be. That's what we expect it to be based off the things that make it up, 2 protons and 2 neutrons. However, when we actually weigh the mass of one helium nucleus, and I'm not going to go into now how scientists can work that out, but when scientists work out what the mass of a helium-4 nucleus actually is, they find out that it's actually 6.65 times 10 to the negative 27 kilograms. So what's gone on here? If we add up the mass of 2 protons and 2 neutrons, we get 6.68 times 10 to the negative 27 kilograms. But when we actually weigh the mass of a helium-4 nucleus, we get 6.65 times 10 to the negative 27 kilograms. We therefore have what we call, and this is an important piece of terminology here, we have what we call a mass defect. The mass defect is the difference between the mass of the parts and the mass of the whole. Notice here that the mass of the parts is greater than the mass of the whole. We've lost some mass. When those 4 nucleons get together to form a helium nucleus, some of the mass gets lost. The amount of mass that gets lost is called the mass defect. So let's write that down. Mass defect is the mass lost, or let's write it as the mass difference between the whole and the sum of the parts. So the sum of the parts was 6.68 by 10 to the negative 27. The whole was 6.65 by 10 to the negative 27. What we can then do is we can calculate what that mass defect is. So I'm going to leave that stuff down the bottom there. We can say that the mass defect here is equal to 6.68 times 10 to the negative 27 minus 6.65 times 10 to the negative 27. And we would get that the mass defect is equal to 3.35 times 10 to the negative 29 kilograms. That's what we should calculate, roughly that, depending on how early you did your rounding and whatever, but it should be roughly 3.35 times 10 to the negative 29 kilograms. So if we've lost that mass, when we stick the nucleons together to form a helium nucleus, that's the amount of mass that we lose. Where does that mass go? That mass turns into energy. And here's an equation that you've all seen before, or at least heard of before, that you're now going to actually start using. And that is the famous equation E equals mc squared. Einstein's famous mass-energy equivalence equation. Basically, the principle underlying this equation is that mass and energy, they're really the same thing. And when we say in reactions that mass is conserved, or we say that energy is conserved, really, each of those things on its own is not conserved, because mass can be converted into energy, and energy can be converted into mass. They're two sides of the same coin, mass and energy. So what's happened here is when each of my 4 nucleons has gotten together to form a helium nucleus, a helium-4 nucleus, 3.35 times 10 to the negative 29 kilograms has been lost from that nucleus, and it has been turned into energy according to this equation. Let's calculate how much energy was created when that mass was lost. So we can calculate this by doing E equals the mass defect, 3.35 times 10 to the negative 29, times C. Now C is on your formula and data sheet. C is a constant. It is the speed of light, the velocity of light, and it is equal to 3 times 10 to the power of 8. Now, notice that it's C squared. So C squared, just be careful when you put this into your calculator because you need to square this whole thing. So the best way to do that is to put brackets around your 3 by 10 to the 8 and square it. Now, here I have the units here, 3.35 by 10 to the negative 29, that's mass. So units are kilograms. This is a speed, so its units are meters per second. And because I'm sticking in my SI units, and I'm saying this on purpose because we're going to be leaving those units in a lesson later on in this week and using some other units to do the same calculation. But for now, I'm in SI units. I've got kilograms, I've got meters per second, so energy is going to be measured in joules. When I put that into my calculator, 3.35 by 10 to the negative 29 squared, I should get an energy of approximately 3.02 times 10 to the negative 12 joules. And that is my binding energy. That is the amount of energy measured in joules that I have holding my nucleus together and stopping those protons from flying out and being repelled from each other. One last thing that I want to go through with everyone is the binding energy per nucleon. The binding energy per nucleon, I've written that pretty badly, per nucleon. If this is the total binding energy, then it is also useful to calculate the binding energy per nucleon, where the binding energy per nucleon is equal to the binding energy divided by the number of nucleons. So in this example here, this is a helium-4 nucleus. Therefore, the number of nucleons is equal to 4. So if I've calculated my binding energy as 3.02 times 10 to the negative 12, then I would do 3.02 times 10 to the negative 12 joules divided by 4 nucleons would give me 7.54 times 10 to the negative 13 joules per nucleon. Ran out of room to write that there. 7.54 times 10 to the negative 13 joules per nucleon. Now, why is that an important number to calculate? Because, and this is a key principle that we're going to keep coming back to over the next few lessons, the binding energy, the higher the binding energy per nucleon is, the more stable the nuclide. The higher the binding energy per nucleon, the more stable the nuclide. This is going to become really important as we move on to nuclear fission and fusion in the next few lessons, but even relating it back to the stuff we've already done, when we talk about a nucleus being unstable and therefore emitting radioactive decay in the form of alpha, beta, or gamma decay, what the nucleus or the nuclide is trying to do is it's trying to have more binding energy available for each one of the nucleons that it's trying to squish together into the nucleus there. So by emitting an alpha particle or a beta particle, it is increasing the amount of binding energy available per nucleon to keep the nucleus together. Hopefully everything here was clear. Underneath the link to this video on Connect, there will be I will write for you which practice questions I'd like you to do to practice the skills in this video, and as always, please let me know either in the comments or email me if you have any questions about any of this.